Hello, I'm Ross Tate from the University of California, San Diego, and I'll be presenting to you work I did with Michael Stepp and Sorin Lerner on automatically generating compiler optimizations from proofs of equivalence of programs. I'm going to begin with a powerful optimization technique that we're all familiar with, namely optimizing by hand. Say you've written some simple program which just goes through an image and computes the value of its pixel. The problem here is that the computation for the address of each pixel, although standard, is more complex than it needs to be in this situation, since we're just going through each pixel one by one. So rather, we could use the faster operation image plus plus. So now we have a choice between a program which is easier to understand and manipulate and another program which will execute more efficiently. Ideally in this situation you could just say, okay, we'll make the compiler resolve this for us. That way we can write our simple program but execute our fast program. The problem is that many standard compilers, such as GCC03, don't actually perform this optimization, so this option may not be available to you, in which case you're stuck between the choice between a program which follows good software engineering disciplines and another program which will actually execute faster. So what we've designed is a technique so that when you're in this situation, you can say, okay, I'm going to train the compiler to do this optimization for me. So that way, whenever it sees this original program I've written, it'll automatically rewrite it into this faster program. Now really, you don't want the compiler to learn this exact optimization, since it's unlikely you're going to be writing that exact program over and over and over again. So really, you want the compiler to learn a more general form of this optimization. Something like, whenever you see a program that looks like this, so some arbitrary expression w, some arbitrary expression h, and some arbitrary use of image I times h plus j, well then the compiler should rewrite this program so that it uses image plus plus instead. Now the compiler shouldn't always use this optimization, since this optimization isn't always sound, meaning it won't always preserve the semantics of the program. So the compiler also needs to know to check side conditions such as h's loop invariant, and this use doesn't modify ij or image. So now what we designed is a technique to make this generalization process automatic. So that way all you have to do is give this example of the hand optimization you want the compiler to learn, and we'll automatically infer this more broadly applicable form. Now, our key insight to making this possible is that this original transformation provided by the programmer is sound. And in particular, these two programs are equivalent. And if we understand why these two programs are equivalent, we can also understand how we might generalize them safely. So let's look at how this actually works. This process all starts off with the programmer. The programmer gives us a snapshot of the program before and after the hand optimization they want the compiler to learn. The first thing we do is we hand off these two programs to a translation validator, which constructs a proof that these two programs are actually equivalent. Not only does this proof ensure that the programmer isn't accidentally trying to teach a compiler a bad optimization, but this proof also contains the information that says which aspects of these programs are important for this optimization to be sound, and all the other details that are important are the ones that are safe to generalize. So now what we do is we hand this proof off to a proof generalizer, which analyzes this proof and constructs two generalized programs, and a generalized proof that these two programs are equivalent. Because these two programs are equivalent, whenever we see an instance of this top program, we can safely rewrite it to an instance of this bottom program. In particular, the original transformation specified by the programmer is just an instance of this generalized transformation we constructed. With this process, we provide a means for the programmer to actually teach the compiler new optimizations with just one concrete example of the optimizations we want the compiler to learn, and using only a language that they already know. So now, let's look at this process in some more detail. Suppose the programmer gives us the optimization, rewrite 8 plus 8 minus 8 into 8. The first thing we're going to do is hand off these two programs to our translation validator to check that this optimization is actually sound, giving us a proof that 8 plus 8 minus 8 actually equals 8. Before we move on to proof generalization, we should at least look at what this proof actually looks like. As with all good proofs, we're going to start off with knowing absolutely nothing. Fortunately, we have an axiom that says anything minus itself equals 0. So we can instantiate this axiom with x as 8 in order to learn the fact that 8 minus 8 equals 0. And in our proof, we make the note that we use this axiom in order to add fact 1. Next, we have another axiom that says, well, if we know something's equal to 0, then anything plus that will equal itself. So we can use the fact that we just learned in order to learn a new fact that 8 plus 8 minus 8 equals 8. And in our proof, we make the note that we used fact 1 in order to apply this axiom, and in doing so, we added fact 2. Now, we've just constructed a proof that the original transformation provided by the programmer is actually sound. And so we can move on to proof generalization. We've actually found that proof generalization works by going backwards through the proof. So we're going to be going from right to left. The first thing I need to do is get these axioms out of the way. And we're going to start off with some general program A transformed into some general program B. And we want this transformation to be sound, so we need to prove that A equals B. The way we're going to do this is by looking at our concrete proof that we just constructed to figure out how to refine A and B so this transformation is actually sound. As we do this, we're going to maintain an invariant that this will be the most general transformation justified by the portion of the proof that we processed so far. Since we haven't processed any of the proofs so far, we start off simply with the most general form of a transformation. So now our first goal is to prove A equals B. And fortunately, we can look at our proof to see that we applied this axiom. So there has to be some C in D such that we already know C equals 0, and we use this to infer that D plus C equals D. We can look at our notes and see that we use this axiom by using fact 1. So C equals 0 must be fact 1, and we can add these to our databases as a future goal to complete. Next, our other notes tell us that we use this axiom to add fact 2. So D plus C equals D must be fact 2. But we already have a fact 2, namely A equals B, and so to resolve this conflict, we need to unify these two facts. In particular, we have to take all the uses of A and substitute them with D plus C. And we have to take all the uses of B and substitute them with D. Now, D plus C equals D is fact 2, and so we can actually copy our notes to say that we use this axiom by using fact 1 in order to add fact 2. Notice that we've restored our invariant, that this is the most general program justified by the portion of the proof we just processed. However, this transformation isn't yet sound since we haven't actually finished processing the proof. So our next goal is to prove that C equals 0. And again, we can look at our concrete proof to see that we applied this axiom. And so there has to be some E such that E minus E equals 0. Now, this axiom makes no assumptions, and so we can start off with the empty database. This is what you'd expect from a good proof. Next, our notes tell us that we use this axiom in order to add fact 1. So E minus E equals 0 must be fact 1. But once again, we already have a fact 1, namely C equals 0. And so we can unify these two facts by taking all the uses of C in our proof and replacing them all with E minus E. Now, E minus E equals 0 is fact 1, and so we can copy our notes to say that we use this axiom in order to add fact 1. In doing so, we've just constructed a generalized proof that these two generalized programs are equivalent. And our original proof is simply a concrete instance of this generalized proof with D and E as 8. In constructing this generalized proof, we managed to transform our concrete optimization provided by the programmer into one which is more broadly applicable. In short, we've just learned an optimization by examining a proof that these two original programs provided by the programmer were equivalent. We did this by handing these two programs off to our translation validator, which gave us a proof that these programs are equivalent. This particular proof relied on the fact that these two 8s were the same, and also on the fact that these other two 8s were the same. So we handed this proof off to a proof generalizer that actually maintained these equalities in our generalized program. However, our proof didn't need all the 8s to be same, so we could actually use two different symbols, D and E, in our generalized transformation. In fact, this is actually the most general optimization for this proof, meaning we can't weaken any of our assumptions and still have the same proof strategy apply. Now the proof generalizer is really the key component of this whole process, but the algorithm I showed you earlier was rather syntactic in nature and used a rather limited logic. Actually though, we formalize this process as an abstract algorithm, expressed in terms of category theory, using basic concepts such as pushouts and pullbacks, and also our own concept which we call pushout completions. This layer of abstraction allows us to adapt our proof generalization algorithm to different logics by using a different category for each logic. In this way, we can use different representations of programs, and we can even apply proof generalization to domains besides program optimizations. At this point, I'd like to show you a number of applications and evaluations of this proof generalization technique. I've already shown you how we can apply proof generalization in order to train the compiler, using this process as described earlier. However, the logic I showed you earlier is too simple to learn powerful optimizations, so we need a more expressive logic. In our implementation, we actually use program expression graphs, which I presented last year at POPL. These are capable of representing both branches and loops, and also expressing side conditions such as loop invariants. With this more expressive logic, we were able to learn optimizations such as interloop strength reduction, which is the optimization I showed you at the beginning of the talk. We were also able to learn a number of other optimizations, many of which aren't done by standard optimizers such as GCC03, justifying our need to be able to train the compiler. A key note to take away is really we can learn any optimization which can be verified by translation validation. So as the technology for translation validation improves, so will our ability to learn optimizations without any additional effort. We've also found that we can apply proof generalization in order to speed up the optimization process. Say you've got some advanced optimizer, such as the many super optimizers being researched right now. This thing is smart, but it's also slow. And I mean really slow. We have a whole bunch of code we want to compile, but we don't want it to wait forever. Now there's also these rewriters out there, which can be over an order of magnitude faster than these advanced optimizers. Ideally what we want is to have both the intelligence of the advanced optimizer and the speed of these fast rewriters. The way we accomplish this is we ship off just part of our code base to the advanced optimizer, which improves this code very well. And then we're going to use our optimization generalizer in order to learn additional rewrite rules. However, the advanced optimizer is actually going to be applying many optimizations in order to produce this final result. So we also use a decomposer, which is able to break down one large optimization into a bunch of small optimizations. In this way, from examining this one optimization, we're able to learn a large number of rewrite rules. Then we incorporate these rewrite rules into our rewriter, essentially incorporating the intelligence we learned from the advanced optimizer into our rewriter. And then ship off the rest of our code base to this fast rewriter to produce their optimized code base, which is then joined by their advanced optimized friend. Now to evaluate whether this process is actually effective, we ran this on a ray tracer, and we actually found that by just training on a small portion of the code with the advanced optimizer, the fast rewriter was able to produce code of the same quality as the advanced optimizer, thus accomplishing our goal of having both the intelligence of the advanced optimizer and the speed of the fast rewriter. Now, as I said earlier, we actually express our proof generalization algorithm abstractly, and so we also wanted to see how this could be applied to domains besides program optimization, although we haven't actually implemented these other applications. For one, we found that we can apply proof generalization to databases in order to learn database query optimizations. We also found we could apply it to Haskell in order to prove the error messages that Haskell gives programmers when their code fails to type check. We also found out that it can be used with code contracts in order to assist programmers with understanding why their programs and contracts are broken. Next, we found we can apply it to type checking in general in order to infer polymorphism and type check programs, even in languages that don't have type inference. Thus, with this one tool, we're able to solve problems from a variety of domains. So to conclude, we've designed and implemented an algorithm for learning compiler optimizations, either from programmers or from super optimizers. And in doing so, we designed an abstract proof generalization algorithm, which can be applied to other logics for reasoning about programs, and even to other domains entirely. Thank you for watching this presentation, and I hope you enjoyed our research.